Hi everyone, in this video we're going to dive into Azure Container Storage v2. Now I previously did a video on the v1, but now the v2 is released. I wanted to go through really what are the big changes. Now if I'm using Kubernetes, if I want to talk to some kind of storage, we use the Container Storage Interface or CSI drivers. Now, these drivers give us access to many different types of storage. So it's a nice standardized way to really talk to any kind of storage. When I'm using Kubernetes across different hyperscalers, it really doesn't matter. So we have these great CSI drivers available. So ACStor v1 allowed for some more advanced backend storage options compared to the options and capabilities that were exposed through CSI drivers. So if I think about the ACStor v1, which again, this is when now I'm talking to Azure Kubernetes service, which obviously is using Kubernetes, it provides a managed experience. So with the AKS, I can now use this ACStor v1, and it would expose other types of storage. Specifically, what it would expose was ephemeral. So the ephemeral storage was the local storage we find on the nodes that's actually powering our node clusters that run the pods that contain the container images. So we could use these local storage from the nodes. It would make it very easy to use that ephemeral storage in the node. And that could be of type SSD or the much higher performance NVMe for those types of actual nodes that had that. It also would expose the Azure Elastic SAN. So that was an iSCSI-based target that I could have various types of storage pool powering it behind the scene. It also gave me access to manage disks. Now, to be clear, there's also CSI drivers for managed disks. So you had choices here. And really what happened with the managed disk type is that it broke some of the one-to-one mappings we had to have. So if I use the CSI driver, I can have one persistent volume per managed disk. So that's all I could do. When I used the ACStor v1, I could actually have, for every one managed disk, I could have n number of persistent volumes. So it gave me some more advanced capabilities there. And so very commonly though, for this ACStor v1, this ephemeral storage was a very popular option because it's very high performance, has a super low latency because it's native to the node. So if I had a very latency sensitive app, if I had a very bursty type app that needed high IOPS, high throughput, it was a really good fit. The Elastic SAN was really good when I needed a more scalable storage, but it was, obviously there's a price attached to that, but I could share performance across multiple volumes, etc. And then, yes, we had this managed disk support, but honestly, most people were just using the CSI driver. The advanced capabilities I got, such as this 1-to-n number of mappings, it just wasn't particularly highly utilized. Okay, so that was the v1. So what is happening with the ACStor v2? So now we're looking at our brand new option. And basically what's happening, at least initially, is that support for managed disks is being dropped. Again, most customers just use the CSI driver anyway. And for the most part, they're willing to sacrifice capabilities at, for example, logical persistent volumes per managed disk. Don't know if it will ever be supported, but it's gone for now. So what's really the focus right now is that local ephemeral disk. That is the huge focus. So what we're going to think about is that local storage that's present in the nodes. And very specifically this time, it's not just local, it's only local if it is NVMe. So whereas before it would use both the SSD and the NVMe, like type connection like SATA, etc., could be general SSD, it wants the NVMe only this time, because that's really the focus of the ACStor v2 is very high performance. And NVMe tends to be about 5 times the speed of a comparable, just regular SSD. Now, what that means in terms of the virtual machine SKUs that we can use, well, it's the L series. So the L series are the storage optimized SKUs. So I can use the L series. Some of the GPU optimized, like the NC series, but also some of the newest versions of things like the D and the E, the general purpose and the memory optimized, they have those as well. So if we jump over super quickly, if you go and look at the VM SKU information, if we scroll down, well, it will say the word NVMe somewhere in this whole list. So here we go, local NVMe storage. And then if we go and look at the specs, it will talk about how you get a certain number of those disks. And it basically can expose these silly amounts of IOPS and silly amounts of throughput. And basically based on the size, you're going to get a different number of disks, which is kind of showing you right here. But also if I was to look at, for example, the NC series, that's also going to say the word NVMe somewhere in here. And so once again, I get a certain number of these NVMe disks. And even the DV6, so it's the little d which has a temporary disk, well, its temporary disk is NVMe as well. And so you get these capabilities now. So we've got right here, faster NVMe. So once again, we have that capability around using those. And it talks about, again, you get different numbers of those with the various IOPS, the size, and you're going to get various throughput as well on that final column. So there are a number of different virtual machines that have these NVMe disks, and they're the ones I have to have. So if it's just regular SSD, it is not going to work for this. So we can actually go and look at an example AKS cluster I have where we've enabled this ACStor v2. So we can see here, looking at the extensions, that I have got the ACStor v2 installed. If we jump over to the node pool, we'll see that I am running an L16S v3. So that's going to give me 2 of those NVMe disks. And if we look at the AKS cluster itself, we can see the Azure Container Storage driver is available and showing us the local storage. Now, by default, the way this is going to work, if we think about for a second the physical node. So if I imagine it's the node, one of the nodes in the node pool. A bit more space. So this is just a node. But remember, of course, there can be many nodes. This is node 1. But I can have n numbers. So I can have node n over here, depending on the size of the cluster, whatever that might be. Now, within this node that is using these NVMe disks, well, obviously, I have those disks. So I have maybe 2, 1, 4. It depends on the exact size of the exact SKU. But these are all my nice NVMe disks. What it's going to do for no matter how many disks I have, it's going to create a RAID 0 stripe across them. Now, RAID 0 means it's not using any of the space for parity. So I'm not losing any capacity available on those disks. But what it means is no matter how much of the capacity I use, it's still going to stripe it across all the disks. So I'll still get all of the performance for the disk. So if we create a persistent volume, in this case, let's go and create a persistent volume. I create the first persistent volume 1. Persistent volume 1 will actually be created across that entire, however many disks there are. So even if it was a fairly small size persistent volume, the performance I get from that potentially very small persistent volume is the IOPS and the throughput that all of the NVMe disks on that node are actually capable of. So I don't have to fill the disk and then I create a second persistent volume. Well, that also is going to be spanning all of the disks and 3, 4, 5, etc. So I just get all of the performance without having to fill all of the capacity. And I can create n number of persistent volumes as much as I want. And then just the regular pods would apply. So, hey, great, I've got all of that. I would now go and create pods. So this is just a pod. And then it would have a persistent volume claim as normal, which would go and map and use one of those persistent volumes. So what's happening here is a number of different things. By leveraging this ephemeral storage, I'm not having to pay for a managed disk. Sure, potentially, if I used UltraDisk behind the scenes, I could, it depends, it'd have to be really big, start to match the performance and the IOPS of what we get out of this. And yes, maybe then also I can get the sub-millisecond latencies, but that's a huge cost compared to, hey, just using that local NVMe storage. And many organizations have virtual machines with NVMe, but are not maximizing it. So the goal really here, and what I'm getting out of this, is this local NVMe is super fast, and it's very, very low latency. I mean, that's the value proposition of using this. So any type of workload I have where I want super low latency, super high throughput, super high IOPS, this is a great fit. Now, if we think about, well, what could that actually look like then for a workload? So think of caching layers. Now, ordinarily, caching would try and use the memory because memory is super, super high performance. But imagine I'm trying to cache something that exceeds the amount of memory available. So if I had like a Redis or a Valkey, for example, well, any type of caching workload would be a great fit here. Another option is things like databases. So PostgreSQL, that open source offering, I did a video on this just last week. Well, that would be able to take great advantage of these very low latency, very high performance. AI workloads, like there's the Keto AI toolchain, where it could cache the model weights, so it would reduce all of the different latencies involved with that. It could load in a model time 5 times the regular speed. So there's a lot of tight integrations between, hey, the ACStor v2 and things like Keto, and the workloads go on. But if you think about, hey, bursty, very low latency, it's going to be a great fit. However, something is probably occurring to you right now. I'm just drawing pictures of local disks in a local node. And we emphasize the word local and ephemeral, i.e., it's not super durable. If the node failed, I have lost the content. If I deallocate the virtual machine, I lose the content. So one of the things we have to think about is if I do care about the state that is being stored in here, I have to handle it some way. And what that way is typically going to mean is some kind of replication, some kind of backup, some kind of copy associated with that. Now, it could come in many, many forms, because the whole point here is native replication between nodes at the sort of the disk layer is not part of ACStor v2. Because for the most part, it's much better to use an app level replication instead of using a storage level resiliency. So I want to defer those things actually to the application itself. Now, maybe what's happening here, the workload running in the pod is actually not the primary copy. So maybe the app has some primary somewhere else that does use a highly durable set of data. And really what's happening here, maybe this is just like a read replica, for example. So I don't actually care about the durability of that storage. Or maybe what I need to do is I would think about having, well, another pod on another node. And I would certainly now want to think about either I'm using availability zones to separate them, or potentially, because it's app level, this is a completely different AKS cluster in another region, and I'm using asynchronous replication. Obviously, there's a slight risk of data loss in an unplanned disaster, but that's something maybe I'm considering. So my other option here is I would do an app level replication. I could do synchronous within the region across AZs. Cross-region, I would use asynchronous options. There's also options maybe that, hey, I'll do backups. So maybe I'm backing up to Blob as part of an app backup capability. Like if I'm using Postgres, for example, there's abilities there that I can dump things out to a Blob database. So Barman, for example, with PostgreSQL, I could go and easily dump that out. The point is, I need to take responsibility if I do care about the state of the content that is on this disk because they're local to the node. Now, all storage fundamentally are disks within a node, but for example, Azure Storage guarantees 3 copies of it spread over nodes in different racks within the cluster. So that gives us a certain level of durability. And if I shut down workloads, it doesn't delete it. These are disks in a node, but it's just disks in a node. So you need to go and add the durability, and that can be added in many different ways. Remember, if my durability is being enabled by the fact that I just have multiple copies of this pod on different nodes in different AZs, maybe different regions, you still should make sure you have a backup and make sure you never shut them all down at the same time. Because if you shut them all down at the same time, all of the storage gets deallocated and you would lose the state. So just bear those things in mind as you look at the different use cases to actually leverage this. But for caching, Cato, and again, in databases, it's a fantastic option. Now, as we talk about the actual performance of this, I said it's very, very fast. Now, compared to the V1, it's actually up to 7 times the performance via the V1 version of this. So they've made like huge changes. And part of that is because the V1 was actually a fork of OpenEBS's ACStor, whereas V2 is a complete rewrite of the architecture. It's not a fork, so there's no etcd database dependencies, there's no local volume manager dependencies. It's just completely rewritten to be super, super optimized. In the V1, you had to configure the number of vCores. I think it capped at 1 GB of memory. In V2, there were no performance tiers. You just get the best performance on a much sleeker performance profile. It has a negligible amount of processor usage. It's still going to saturate the memory up to 1 GB, even at idle, because it's kind of planning ahead. It's working out how it can best use that memory. Now, what would be fun is, well, exactly how very fast is it? And so we're going to go and do a test against that cluster. Remember, that only has 2 NVMe disks. So let's do basically a complete benchmark against it to see, well, how many IOPS and throughput can we get?
Okay, so we're going to run an IOPS performance test. Now, this is going to take a couple of minutes. So through the magic of editing, we'll be able to skip all of the wait. Okay, so the test finished. And what we can see here is from the read statistics, we actually got a bandwidth of just below 5 gigabytes per second. But if we scroll up, we should see the IOPS details. Okay, so the IOPS actually minimum 506,000, maximum 2 million, but the average was about 1.2 million IOPS. So a pretty crazy high number that we're doing. And again, this is just with the 2 local NVMe disks, which it's striping across.
Okay, now, actually what's happening behind the scenes is this local access is actually a CSI driver that Microsoft have written. So they wrote a CSI driver to expose local storage, and they did actually open source it. So if we jump over for a second, you could actually see this is that local CSI driver that Microsoft have open sourced that gives me access to that non-durable, that local storage in a node. So what I could absolutely do is if I have a self-hosted cluster, so I've got some Kubernetes that is not AKS, I can actually still use this. I would install via a Helm chart, whereas in AKS, obviously, it's just an extension, but it would have all the same features striping across the disks. So Microsoft's goal here really is to expose more types of storage to customers. And this is just an easier way to now take advantage of that storage that potentially I'm already paying for. And remember, Azure Container Storage v2 is providing a management layer on top of that local CSI driver and whatever future storage drivers they make available. So ACStor is making it easier. I just install the extension AKS and it's available to me. Now, some other changes. I talked about nodes down here. So there is no longer a 3-node minimum. I could have one node, I could have a dual node, because again, it's not doing the storage, it's not doing replication. And when I do replication, I like 3 nodes, so I can get that certain guarantee and resiliency to it. But because it doesn't do the replication, and instead I'm doing my application level, there's no node minimums on that anymore. There are also no fees associated with it anymore. So whereas I would pay once I've reached a certain amount over here, well now, it's just free. I'm not having to pay for anything related to that. I just choose and use it, whatever I need to do. I just want to use the underlying storage. Now, obviously, there was Elastic SAN support over there. So what should be happening in the future, so post-GA, we should see that Azure Elastic SAN will get support. If I'm already using the V1, there is no direct migration to the V2. There are so many breaking changes, you can't just migrate from V1 to V2. Now, V1 is going to be supported for the foreseeable future, and I cannot run V1 and V2 on the same cluster. So you're making a choice between those. But obviously, this is the future direction. But hey, if I'm using these features right now, great, stay on ACStor V1. But think as you go on, hey, where's the opportunity to start and taking advantage of these enhanced capabilities? So there you have it. Really today, the focus of this is all about those local NVMe disks. So I get that very high performance, that very low latency. The ACStor v2 takes away all the management overhead and the details of using that local storage. But hey, more workloads are going to come in the future as it adds things like Azure Elastic SAN. Hope that was useful. Until next video, take care.